So decision trees, what is the root problem of that decision trees aims to solve? Let's say decision trees are a supervised learning algorithm that learns to extract rules from data directly. So decision tree is nothing, just aims to find the split, aims to find a split that separates out the classes, separates out the classes that separates out the classes homogeneously. Let's say if there is some data where we have some cross and circles, so decision tree finds a split on a feature f1 that splits this and this home at the best. So the split should separate the data homogeneously, and if data is very complex, we'll try to make n splits like this on multiple features. So let us see how things are. So information greedy approach. So decision tree is information greedy. Why? Let's say we have a example where we have BP, HR is heart rate and temperature. So we want to learn the condition to segregate normal from abnormal patients. So we don't know the range. Let's say we are in some, you know, the BP, heart rate are just introduced. We don't know these features. Let's say we are in some 1500s or so. So a new patient comes in, and with we measure with the meters. We have 130, HR is 80 and temperature is 101. So we need to predict whether the patient is normal or abnormal. So from the symptoms, which is our symptoms, from symptoms we have to predict the target. Which symptoms will lead me to the target with maximum certainty? Analyze symptom of I has how much randomness or uncertainty. So we don't know which symptom will give me the maximum certainty, but we have the data. We have the data that, let's say symptom 1 is BP, symptom 2 is heart rate, and symptom, what is this last symptom is temperature, right? We have some data of some patients, and this date we also have the target, right? This is the historical data. The problem was from 1500s, but the solution came in 1600. Let's say we have 100 years ka data. Now we can build a decision tree on it, but doing the manual approach is very it's very boring, and we don't do it, and very lengthy also, very lengthy. So we train the machine to do it, right? 1600 is much less number. Let's say we are in machine learning era. So we are in 2000, we are in now 21st century. Let's say now in the 21st century, how do we extract the rule, right? Let's say BP is somewhere around 90, heart rate is also 95, and temperature is around 100. The patient is normal, which is 0. Let's say again BP is 95, heart rate is 100, temperature is 99, patient is normal, right? So, and we have more data also here, here and here. Now I want that if BP, heart rate, temperature or target, which of the following features of the following which of the feature will give me a split between the 0 and 1, which is my target, right? The target would be a BP, right? So let's say BP ranges from 80 to 120. I don't know whether the BP ranges from normal. BP range is 80 to 120, right? So 80 to 120, right? And we have the data as a histogram plot like this. Majority have a BP of 100, right? Frequency. But we don't want the histogram plot, we want whether this BP ka range is able to give me the target, able to segregate the target from the target. Let's say patient is 0 here and some zeros are here also, some zeros are here and some ones are here. I don't know because BP is not a direct indicator if the patient is normal or not. So let's say it is high, it cannot tell whether the patient is normal or not. It can, create a split somewhere around here or somewhere. That is too much. Let's reduce some zeros from here. So let's say 100 से ज़्यादा वाले 1 निकाल देते हैं हम यहाँ पे 0 0 0, यहाँ पे 1 2 0, right? So we can say there is split here, but we cannot, depending upon the data. So how do we measure the uncertainty? How can we measure the uncertainty? So uncertainty is generally calculated by Gini, which is 1 minus summation of 1 to C. C is the number of classes, P of I ka square. So proportion of class present here. So let's say we create a split here and number of samples present in the left and right. Let's say these are normal and these are abnormal patients. So we have 5 patients out of how many here? 1 2 3 4 5 6 7. So 12 patients into, no, this is entropy, sorry, this is 5 by 12 ka square plus 7 by 12 ka square. So whatever the value would be my uncertainty. So after split, this is after split uncertainty 1 by 25 by 144 plus 49 by 144 will give me 1 minus 20. This is 60 plus 74 144. What is 74 by 144? By 144, this is 0.51. So 1 minus 0.51 will give me 0.49, right? So as the Gini index lies between 0 to 0.5, 0.5 means data is very much you know heterogeneous. There is a 50-50 split between classes, so we cannot tell, this feature cannot tell with certainty, or this feature and this threshold cannot tell with certainty whether the patient is normal or not, cannot segregate the class. So this is how we compute the uncertainty, and then we pick a feature and a threshold that is belonging to that feature, which gives me maximum information gain. Well, what is information gain? Information gain is nothing, just the uncertainty before split minus uncertainty after split. That can also be written as parent Gini minus weighted child Gini, right? So we can calculate the entropy, the measure of uncertainty, using the entropy formula also, or using the Gini formula also. Gini is much more used in industry because of the simplicity. Gini is used more because entropy has log in it, and calculating the log is computationally heavy. And Gini lies between 0 to 0.5, where 0.5 indicates a maximum uncertainty and 0 indicates minimum uncertainty, where entropy lies between 0 to 1. 0 to 1 for binary, and 0 to log 2 to the number of classes for the multi-class. Now information gain is just parent entropy minus weighted child entropy, right? So let's say for our data set, temperature less than 100 is my first split. If I split based on temperature less than 100, we get two possibilities, right? Either temperature is less than 100 or greater than 100. If yes, then we check if the temperature is greater than 98. If it's again a yes, then we have 20 samples which are belonging to normal class, which is class 1 or class 0, I don't know. I don't remember which class I took for this normal. I don't know, right? But the thing is, using this formula, we calculate the uncertainty, and uncertainty is whichever feature threshold gives me the best reduction in the uncertainty, or you can say maximum information gain. Both are the same thing. Maximum information gain or maximum reduction in Gini in uncertainty. Yeah, maximum information gain or maximum reduction in uncertainty, that feature threshold would be my splitting condition. So let's say if I choose first splitting condition as temperature less than 100, then I choose temperature greater than 98. Yes, we can use the same feature again because it gives me the maximum information gain. We can use the same feature, right? But at a different threshold, of course. And we reach the homogeneous. So this is my homogeneous leaf, right? So we should the model focuses on splitting the data such that the leaf nodes are homogeneous, because homogeneous uh, so the leaf are responsible for making the prediction. Let's say we have reached the max. This is level 1, this is level 2, and this is level 3. So in 3 splits we have arrived at a leaf node after 3 splits. After 3 splits is nothing but just the 3 conditions. 3 conditions: temperature greater than 100, temperature less than 98, and just 2 conditions, right? So, and my entire prediction relies on temperature. If the temperature 98 to 100, yes, then I'm predicting the patient is normal. If temperature is not less than 100, it is greater than 100, then we are checking heart rate greater than 100. If yes, we are left with the imbalance leaves. These are also leaves. These are also leaf. This is also leaf. But if the patient goes in some of satisfies the condition of these leaves, we go with the majority. Let's say here is a 4 4 50 50 prediction. It is 2 4. 4 belongs to the abnormal part. So the majority vote will be abnormal. Here it is a balanced, and here it is also balanced. So generally this balance criteria doesn't happen in decision tree, because the decision tree looks out for the maximum reduction in variance, reduction in the uncertainty. Yeah. So for a new data, let's say we have this data: BP 130, HR 80, and temperature 101. So we look at the temperature first. Temperature less than, no. So HR was how much? HR was 130. HR was 80. BP is 130. Okay. HR 80, BP 130. So for HR 80 greater than, no. So we arrived at this. So here we have no other depth. We are left with 4 samples. So we cannot say whether the patient is normal or not normal. We are with 50-50 prediction. So we need this. Tree is a underfitting tree. It cannot predict this. So we need to add more depth. We need to increase the depth so that my model is able to capture the complex patterns from the data. So what are the limitations of this tree, or what are the patterns that decision tree has? Let's say decision trees are highly interpretable, just like linear regression. The weights can be interpreted, or the path to decision can be interpreted very easily. So what led to the decision can be interpreted, which is very useful for medical use cases, or e-commerce. Any use case we can take where the interpretability is a concern. We can use the decision tree, and we can plot also using the scree plot the decision examples. Less data pre-processing, no scaling or standardization, as we are not concerned with the you know comparing the features. We are just concerned with the which feature threshold value gives me the maximum reduction in information gain. That is my best that is my splitting criteria. Right. Prone to overfitting, as model can split each and every sample. Yeah. So if the model keeps on keeps on growing as max depth is infinity, it can form rules that are that are not generalizable. It can form rules which are over optimized for my over optimized to my data training data. So we need to control this hyperparameter in order to control the depth of the tree, control the splitting criteria. If yeah, else the tree would grow too high. If the tree would grow too much, it would be an overfitting criteria. Max depth, number of splits, high would result in overfit, low will result in underfit. Okay, complex and simple decisions. Min sample split is also a hyperparameter here. If the number of samples required to split the node further, if this variable is high, the, the resultant split would be less. If this variable is low, the splits would be higher. As let's say we have 10 samples and we split that samples into 5 more samples and we do a 2 3, so the number of splits would be more, right? The minimum samples in leaf, so let's say here we have 2 samples in leaves, here we have 3 samples in leaf. But if you don't control that, this 2 would be might be very much overfitting, and this 3 is also leading is indicating the overfitting scenario, because we cannot form a rule just to get 3 samples, just to get 2 samples. So both of the mean sample split and mean sample leaf are important to control the number of splits. Now if you have 60-40 prediction, majority vote 60 wins, that is also thing. What about outliers feature? Let's say we have a feature that has outliers. Yeah, so let's say a feature value temperature has an outlier of 108. Then what happens? It doesn't really matter, because as if my feature ranges from 96 to 108, right? 96, 97, 98 up to 108, I only need to find a threshold value from that feature. If the threshold value is like, let's say 96.5, 97.5 or so, if I have an outlier of 108, it doesn't affect my threshold value. I just need to find a threshold value that is giving me the maximum information gain. If that threshold value is giving me if the outlier is giving me a maximum reduction in uncertainty, then it is good for my model to separate out that outlier from the remaining data set. So it is not a concern. The concern here is if my target variable has a outlier. Let's say here we have 2 classes, but when we are dealing with the regression problem, and regression problem are having high range, let's say 0 to 50k, so it's not a high range, let's say 50 million, right? And I have a outlier of 500 million, so my decision tree would be forming rules to isolate this outlier, which will result in overfitting, because the rules are not generalizable, but it is for treating the outlier which may not be present in other data set. So therefore we need to handle the outliers first for the regression task. But we have another methods to handle this also. Let's say we have a numerical value as a feature. Let's say here we have temperature. So let's say we have another numerical value which has a very high range. What we can think, temperature, BP, anything, you know, BP, 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 BP. Let's say we have BP. Generally BP ranges from 80 to 120, but I have some 200, 300 BP wala samples. So 80 to 300 will give me about 220 thresholds approximately. So my model would check the Gini at each and every threshold. So that would be a huge calculation. So therefore my model creates bins, let's say 80 to 100, 100 to 120, 120 to 140, and so it would reduce this 220 values to distinct number of bins, let's say 8 to 10 bins, and check which of the following bins has the least has the maximum reduction in entropy. Right, this is automatically handled in decision trees. Okay, feature importance, we can also get feature importance out of the decision trees. It's from how do we get the feature importance from the decision trees? The number of feature used to make a split, that causes the reduce in uncertainty, means that feature is important. Let's say I use the temperature variable 2 times, and 2 times how much my uncertainty was reduced for the target variable, which means this feature explains my target well because it has higher number of splits. Therefore we have a formula to calculate the feature importance for each feature depending upon the number of splits it makes and how much it reduces the uncertainty. Therefore we have a formula for it. Using that formula we can calculate the feature importance for each and every feature. Model evaluates the weighted entropy reduction using a feature. I have not mentioned the formula. Where is the formula? Okay, TC, terms and conditions. No, this is time complexity of decision tree. Sorting one feature. Yeah, so first we need to sort the features, right? Sort the features, only the numerical, categorical features don't count. Yeah, sort the features. Once sorting is done, then we identify the best split. Okay, so n log n to sort one feature, and we have d features, so d into n log n plus the identifying the best threshold takes O of n. Why it takes O of n? As we compute the Gini of proportion of ICA square, right? So for first threshold, let's say temperature 96, left has 0 samples and right has, let's say, 100 samples. So we store this value, left equals to 0, right equals to 100. Now if you take another threshold value as 97, so we just update these pointers. We don't count everything again. So the time complexity of updating those counter this pointers is O of 1. So for n values, checking for n values, let's say if we have n values, we need to check for n minus 1 thresholds. So the time complexity becomes O of n into n minus 1. But as we know that computing for n values is not required, we just need to update the pointers, it becomes O of 1. So we are left with O of n minus 1, which can be written as O of n. Generally because why it reduces from O of n to of n to O of 1, because we have sorted everything and we just need to count the left and right samples in counters. How many target variables are to the left and to the right? We just need to count this, and we have the genie. So just to update this, we don't need O of n, we just need O of 1 practically. Therefore it is O of n, and O for sorting it is d into n log n, and this is O of n. So we can, it is just a addition, so we can write complexity as d into n log n, a decision tree for the entire decision tree at each split. So if it makes n splits, it would be n into this. Thank you.